When you're following the world of large language models, it feels like, well, it's easy to get bombarded by just the numbers, right? Billions of parameters, huge context
Oh,
windows.
absolutely. Constant stream of bigger and bigger.
Yeah, and you start wondering, okay, beyond just the raw scale, what are the real shifts happening? Like the fundamentally new ideas pushing things forward?
What are the actual academic contributions, you mean?
Exactly. How do you cut through the noise and see, the real scientific or engineering progress?
That's such a crucial point. Things move so fast. And understanding those underlying breakthroughs is really the only way to tell genuine advancement from just, well, turning the crank.
Well, today we're going to try and do just that. We're going to zero in on a development that's definitely catching eyes, especially in the research community.
Okay.
We're doing a deep dive into Pangu Ultra. It's a dense LLM from Huawei, and, well, they're making some pretty significant clips.
Right. Pangu Ultra. Yeah, the reported 135 billion parameters definitely puts it up there with the big dense models.
Mm-hmm.
But I think what makes it particularly interesting, maybe from an academic angle, is the whole package. It's not just the size. It's the architectural decisions they made and the system level stuff, how they optimized it for their own hardware, the Ascend NPUs.
Okay, so while the 135 billion number is the headline,
Yeah,
our mission today really is to unpack the innovations. What's actually new here that underpins the performance they're reporting? We want to look at the how and the why, especially through that academic lens.
give folks a shortcut to understanding the core advancements.
Exactly. Okay, let's get into it. Where did they really break new ground?
Well, a really good place to start, I think, is a fundamental challenge you hit when you're training these really big, really deep networks,
Okay.
which is training instability. The loss just suddenly spiking, things going off the rails.
Right, that can just kill a training run.
Totally. And the Pangu team seems to have proposed some novel architectural ideas to tackle that specific problem head on.
Ah, okay. I think I saw something about depth-scaled sandwich normalization. Sounds interesting, like they're trying to manage how signals flow deep inside.
That's exactly it. So traditionally, you often see pre-layer norm in transformers, right? Normalized before the attention or the MLP.
Uh-huh.
But that can sometimes cause issues, especially with gradients in very deep nets. Sandwich normalization, well, it's kind of like the name suggests.
You put the normalization around the layer.
Yeah, you apply layer norm both before and after each of those sublayers, the attention and the MLP. Think of it as just creating a more controlled environment for the signals passing through each block.
Okay, tighter regulation within the layer makes sense. But then what about the depth-scaled part? That sounds specific.
Right. This is where the innovation for very deep models really comes in. In Pangu Ultra, they specifically initialize the trainable gamma parameters. These are the scaling factors in the post-layer normalization steps. Okay. With values that are inversely proportional to the network's depth. So basically, the deeper you go in the network, the smaller these initial scaling factors are set.
Huh, that's clever. What's the thinking behind that? Why would scaling based on depth help stability?
The core idea, the hypothesis, is that by doing this, by initializing these post-norm scales based on depth, they can kind of dampen potential gradient issues, explosions, vanishing gradients as the information flows through, dozens or hundreds of layers.
Right, preventing things from getting out of control way down deep.
Exactly. By controlling the scale of the outputs from each block relative to how deep it is, they think they can smooth out those nasty loss spikes that can just ruin training. They actually have a figure 1, that shows the difference compared to standard pre-layer norm.
Okay, and did it work? Is there solid evidence this helps?
Well, their ablation studies look pretty convincing, academically speaking. If you look at Figure 7 and Table 5 in their paper, they compare models trained with this depth scale sandwich approach versus standard pre-layer norm.
Uh,
And they show much smoother loss curves during training, which is what you want to see. But more importantly, they also show better performance on the actual downstream evaluations.
so not just about smoother training. It actually leads to a better final model.
That's what the evidence suggests. Yeah, it strongly indicates that this depth-dependent scaling really does help stabilize training for these super deep architectures.
Did they also check if it was specifically the depth scaling part that mattered, not just using sandwich norm in general?
They did, yeah. Good point. Figure 8 compares it to just plain sandwich norm. And while regular sandwich norm did help a bit, they found it could still hit those loss spikes when things got really, really deep.
Uh-huh.
But the depth scaled version, it stayed much more stable, kept a more consistent training path. They even give specific initial values like 0.283 for attention output gamma, 0.432 for MLP.
Which suggests careful tuning.
Oh yeah, that kind of detailed hyperparameter work is definitely a sign of rigorous academic investigation.
Okay, fascinating. So, depth-scaled sandwich norm seems like a key piece for stabilizing these ultra-deep nets. What else did they do architecturally? Any other core challenges they tackled?
Yeah, another really fundamental thing they looked at was weight initialization. How you set the initial values of all the connections in the network.
Right, that's always critical.
They call their approach tiny minute. Now, usually initialization methods scale weights based on like the number of input or output connections to a neuron, right? Trying to keep activation variances reasonable at the start.
Standard practice, yeah. So, how is Tiny Emmet different?
Tiny Init brings in a different scaling factor. It explicitly considers both the model's depth, let's call it L, and its width, or hidden dimension, D.
Both depth and width. How?
The standard deviation they use for initializing weight is proportional to the square root of 1 divided by 2 times D times L, so it would 1030 L.
Okay, that's a very specific formula. What's the intuition there? Why depth and width like that?
The hypothesis is that by scaling inversely with the square root of both depth and width, Tiny Init helps create a more sort of balanced starting point for all the parameters across the whole network. Doesn't matter if it's a shallow layer or a deep one.
A more uniform initial state?
Exactly. And the idea is that this more consistent initial parameter scale makes the optimization process smoother, helps it converge faster, and hopefully leads to better generalization in the end.
And they showed this helps too.
Yeah, their table 6 has ablation results showing models using Tiny Init perform better than ones using more traditional initialization.
Interesting. I also noticed they mentioned using something different just for the embedding layers, a standard deviation of zero point 0.5.
Xiaobai. Yeah, that's right. Embedding layers are a bit special, aren't they? They're mapping the discrete input tokens to vectors.
Right, the very first step.
So they often behave a bit differently from the main transformer blocks. The Pangu team found empirically that just initializing those embedding weights with a standard deviation of zero point 0.5 worked well.
Why might that be?
Well, it likely just relates to their specific job capturing the initial meaning. Maybe that slightly different scale helps them be sensitive enough to the input tokens right from the start without causing huge activation variances early on. It's often something you tune based on experimentation.
Okay, so two key architectural innovations. Depth-scaled sandwich norm for stability, tiny init for better initial state. Both seem crucial for just enabling stable training at this 135 billion parameter scale.
Absolutely. Foundational pieces.
Now, let's switch gears to the compute side. Training something this big. I mean, 8,192 Ascend NPUs, that's a massive cluster. How on earth did they make that efficient?
You're right, that's a huge systems engineering challenge. You can't just throw hardware at it. You need incredibly smart parallelization. And the Pangu team used a really sophisticated mix of techniques.
Okay, break it down for us. What parallelization strategies did they layer together?
All right, so they used a combination. They had 128-way data parallelism, basically 128 copies of the model training on different data chunks.
Standard enough, often with something like 0.
Exactly. They used 0 with data parallelism to reduce memory redundancy. Then, 8-way tensor parallelism, splitting individual matrices across 8 NPUs.
Okay.
They also use sequence parallelism, which helps specifically when you have very long input sequences distributing parts of the sequence calculation.
Right, important for a long context.
And finally, 8-way pipeline parallelism. That's where you divide the model layers into stages, like an assembly line, across different sets of NPUs.
Okay, that pipeline parallelism, especially at that scale, doesn't that usually lead to devices sitting idle, those pipeline bubbles?
Ah, you've hit on a key problem. Yes, especially with lots of pipeline stages and high data parallelism, you get significant idle time waiting for the previous stage, big bubbles.
So how did Pangu Ultra tackle that?
They implemented something pretty clever, an interleaved pipeline parallel scheduling strategy. Instead of just one stage per device set, they created, effectively, 6 virtual pipeline stages running interleave on each physical device group.
Whoa, okay, virtual stages. How does that help?
If you look at their figure 2, it illustrates it. By interleaving these smaller virtual stages, they can fill in the gaps much better. It allows for finer-grained workload distribution.
And cuts down the bubble time.
Dramatically, they report reducing the bubble ratio of the idle time from over 30% down to just 6.8%. That's a massive boost in training throughput and efficiency.
That really is substantial. It sounds like a very tight software-hardware co-design. Were there other system optimizations that helped get that efficiency up?
Oh yeah, several other key things. One they highlight is called MC2, stands for Merged Compute and Communication.
Merging compute and communication. What's the academic novelty there? Usually those are separate steps, right?
Exactly. Normally you do your big matrix multiplies and you do your all gather or reduce scatter communication to sync things up for tensor parallelism, for instance.
Right. Compute, then communicate.
MC2 breaks that down. It decomposes both the math operations and the communication steps into smaller chunks. and then pipelines those. It interleaves the small compute chunks and small communication chunks.
Ah, overlapping them at a finer grain.
Precisely. Figure 3 shows the concept. By maximizing this overlap, they can hide a lot of the communication latency behind the computation. It leads to faster execution and better use of the Ascend hardware. It's about breaking down those traditional barriers.
Like threading a needle between processing and data moving? Smart. What about optimizations for the transformer itself, especially you mentioned long sequences?
Yeah, they developed something called NPU fusion attention, or NFA. Basically, a highly optimized self-attention calculation specifically designed for their Ascend NPUs.
Optimized how?
It's particularly good for long sequences, and also handled situations where you need to frequently reset the attention mask, like if you pack multiple documents into one long context.
Okay.
Figure 4 shows how it works. Instead of building a huge, explicit attention mask, it uses a kind of template mask combined with the actual sequence length for each part. This saves a ton of computation and, critically, memory, especially with those 128K contexts.
Makes sense. And did they fuse other operations too, not just attention?
Yes, absolutely. They went for a whole suite of kernel fusions. Things like RMS norm, the Xueyu activation, rope to positional embeddings, gradient accumulation, even the send-receive operations for pipeline parallelism.
The goal being?
Reduce overhead. Every time you launch a separate small calculation, there's overhead. Fusing them means fewer launches, better data locality on the chip, which all adds up to better performance on the NPUs.
Right. I also saw a mention of subsequence partitioning for context parallelism. What problem does that solve?
Okay, so context parallelism, or CP, is another technique for handling super long sequences that don't fit in one NPU's memory. You split the sequence into chunks across devices.
Uh-huh.
But because of the causal masking in transformers, where a token can only attend to previous tokens, the workload isn't balanced. The devices handling later parts of the sequence have more work. Figure 5 shows this imbalance.
Ah, right. The attention pattern isn't uniform.
Exactly. So the Pangu team came up with a load-balanced partitioning scheme. Each NPU actually computes two different chunks within each subsequence. This clever assignment helps even out the workload, counteracting the imbalance caused by causal masking and also those reset attention masks.
Wow, that's getting into the weeds of distributed computing. It sounds like a really comprehensive systems effort. They even optimize mask generation itself.
They did. Instead of calculating attention masks on the host CPUs, they moved that onto the NPUs to cut latency. Remember those interleaved virtual pipeline stages?
Yeah, the 6 virtual stages per device.
Well, the first virtual stage on an NPU generates the mask, and then it just shares that mask with the other 5 virtual stages on the same NPU.
Ah, avoiding redundant calculations. Smart.
Yep, no need for every virtual stage to redo the mask math, reduces compute and memory cost again. And the payoff for all this meticulous system engineering, they report achieving over 52% Model F ops utilization MFU when training on that huge 8,192 NPU cluster.
52% MFU at that scale is seriously impressive. That speaks volumes about the efficiency.
It really does. It's a testament to that tight co-design between the model, the software, and the Ascend hardware.
Okay, let's shift then. We've talked architecture, stability, system efficiency. What about the fuel, the data? 13.2 trillion tokens. That's just vast.
It's an astronomical amount of data, absolutely. But just as important as the quantity is how they curated it and used it. They didn't just dump it all in.
Right. They mentioned a domain-aware vocabulary strategy for the tokenizer. What's the academic thinking there?
The thinking is that different kinds of text, like general web text, computer code, mathematical papers, have very different word frequencies and vocabularies.
Sure, code uses specific keywords, math has symbols.
Exactly. So instead of just counting words across all 13.2 trillion tokens globally, which might let common web words dominate,
Uh-huh.
they first analyzed word frequencies within specific domains separately: English, Chinese, code, math, and so on. Then, they carefully merged these domain-specific frequency lists, deduplicated them, and built their final vocabulary of about 153,000 tokens.
So the goal is better representation for specialized domains.
Precisely. It aims to give a more balanced vocabulary, ensuring that important tokens for reasoning tasks, like in math or code, aren't drowned out by high-frequency words from general text. Table 1 details this domain breakdown. It's a more principled approach to vocabulary building for multifaceted models.
That makes a lot of sense. Okay, so a carefully built vocabulary. What about the pre-training process itself? Was it just one long run or more structured?
Very structured. They used a distinct multi-phase curriculum, 3 main stages, each with a different data mix and objective.
Okay, what were the phases?
Phase 1 was the general phase, up to about 7.4 trillion tokens. Focus here was broad language skills, general knowledge, lots of diverse, high-quality English and Chinese text.
Building the foundation.
Right. Then came the reasoning phase from 7.4T up to 12 trillion tokens. Here, they shifted the focus heavily towards boosting reasoning abilities.
How?
By significantly upping the proportion of high-quality math and code data, they even included synthetic data specifically designed to challenge logical inference.
Interesting. Synthetic data for reasoning.
Yeah. And finally, the annealing phase, the last bit from 12T to 12.8 trillion tokens. This was about consolidating everything, the knowledge and the reasoning skills.
How did they do that?
They emphasized instruction data in this phase, things like curated question sets, examples of multi-step reasoning, chain of thought examples, really honing its ability to follow instructions and reason methodically.
So a clear progression, general knowledge, then deep reasoning, then consolidation and instruction following. Seems logical. I also read they increased the context length gradually during pre-training.
Yes, they did. Started at 4K tokens, then went up. That's a pretty common technique now.
Why did it gradually?
It left the model first.
You know, when you're following the world of large language models, it feels like, well, it's easy to get bombarded by just the numbers, right? Billions of parameters, huge context
Oh,
windows.
absolutely. Constant stream of bigger and bigger.
Yeah, and you start wondering, okay, beyond just the raw scale, what are the real shifts happening? Like the fundamentally new ideas pushing things forward?
What are the actual academic contributions, you mean?
Exactly. How do you cut through the noise and see, the real scientific or engineering progress?
That's such a crucial point. Things move so fast. And understanding those underlying breakthroughs is really the only way.
Oh, hey there, what's up? That's a great point. Let's definitely give you the main takeaways right now.
Absolutely. It's easy to get lost in the details, so let's zoom out.
Okay, so the big picture with Pangu Ultra is it's a really powerful, dense language model.
And it's not just the 135 billion parameters that are important.
Exactly. They've made some key innovations that really stand out academically.
First, to train such a deep model stably, they use depth-scaled sandwich normalization.
That helps prevent those frustrating training crashes,
Right. And they also developed tiny init for better weight initialization.
giving the model a more balanced starting point.
Then on the system side, they achieved amazing training efficiency.
With a super smart combination of parallelization techniques,
And innovations like MCC for merged compute and communication.
plus NPU fusion attention optimized for their hardware.
All of this allowed them to train on a massive scale very effectively,
Their data strategy was also really interesting,
with a domain-aware vocabulary for better representation,
and a multi-phase pre-training process focused on reasoning,
culminating in strong performance on a wide range of benchmarks.
outperforming other dense models and even competing with sparse ones.
So the key takeaway is it's a holistic approach,
Architectural innovations, system optimizations, and careful data curation.
all working together to push the boundaries of dense LLMs.
Hopefully that gives you a good overview of the core advancements.
Now, should we dive a little deeper into any of these areas?
Yep, go on. That's an interesting direction.
Can you clarify what you mean by check the emotion email evaluation?
Are you asking about how well Pangu Ultra performs on tasks related?
Oh yeah, let's hear it.
You want to give us your thoughts on Pangu Ultra?
We'd love to hear what stands out to you.
Based on what we've shared so far, what are your impressions?
What are some of the key things that resonate with you?
Or maybe some areas you find particularly interesting.
Your perspective is really valuable to us.
It helps us understand what's most impactful.
And what aspects we should maybe focus on more,
We were just about to dig into some of the specifics,
like the architectural innovations they made,
starting with how they kept the training process stable.
which is a huge challenge for models this size.
Oh, go for it.
Okay, let's unpack this. You're interested in how Pangu Ultra benchmarked against other top models, right?
Absolutely. That's a fantastic point to focus on.
The paper does provide some really interesting comparisons.
It mentions that on most general English benchmarks,
And on all Chinese benchmarks.
Pangu Ultra actually achieved state-of-the-art performance.
That's when compared to other leading dense LLMs.
Models like Llama 405B and Mistral Large 2,
What's fascinating here is,
that it outperformed Llama on many challenging tasks.
while using significantly fewer training FLOPs.
So it seems like they achieved more with less, in a way.
This raises an important question about efficiency,
Now, it did trail DeepSeek v3 on some code and math tasks,
which highlights that different models have different strengths.
but overall, it performed very competitively across the board.
And in post-training evaluations focused on reasoning,
It actually achieved state-of-the-art results on some really tough benchmarks,
like AIM 2024 and Math 500.
demonstrating the effectiveness of their reasoning-focused training.
So in short, the benchmarks suggest Pangu Ultra is a very strong contender.
Especially when you consider its performance relative to its training costs
It really underscores the potential of dense models.
and how far they can be pushed with the right approach.
Now, were you also curious about specific architectural details?
Because they did some novel things there to achieve this performance.
For instance, to handle the depth of the network.
They used something called depth-scaled sandwich normalization,
It's a way of normalizing the signals within the network.
both before and after